Hello again. In this section, we're going to talk about Cauchy Euler equations. And they're not the same, they're not constant coefficient. They have variable coefficient on the derivatives. But it turns out that we can use sort of a similar process with a different assumption as we did for the constant coefficient equations in the previous section. All right, so let's take a look at them and see how to approach them. All right, so equations of the form ax squared y double prime plus bxy prime plus cy is equal to 0 are equations that are called Cauchy Euler equations. Now, how you want to recognize them, look at the second derivative on y and notice how x is raised to the second power. First derivative on y, x is raised to the first power. So if you see something like that, that clues you in that this is a Cauchy Euler equation. Now for the Cauchy Euler equation, the assumption that we make is that y is of the form x to the r. And like we did for the constant coefficient equations, we will make that assumption, substitute, derive an auxiliary equation, and see what happens. So let's continue with that assumption. So then y prime would be r x to the r minus 1, and y double prime would be r times r minus 1 x to the r minus 2. Using the assumptions and substituting, we have then ax squared times r by r minus 1 x to the r minus 2 plus bx times y prime is r times x to the r minus 1 plus c, and then y we're substituting with x to the r. And we need this to equal 0. All right, so we go through some algebra here. Notice that I have an x to the second and I have an x to the r minus 2. And similarly in the second term I have an x and an x to the r minus 1. So after simplification, we now have a times r minus 1 times x to the r plus b times r times x to the r plus c times x to the r, and we need this to equal 0. So notice now I can factor x to the r out. And let's see, simplifying, I have ar times r minus 1. So that would be ar squared minus ar. And then I have a plus br. And then I have a plus c. And we need this to equal 0. So now, we can either have x to the r equal to 0, which implies that x is equal to 0. That's kind of boring. So let's assume that x is positive. So let's assume that x is greater than 0, so then x to the r cannot equal 0. Let's make that assumption, and let's focus on the rest. Let's focus on this, the characteristic equation, which now becomes ar squared, and I can write the second term as plus b minus a times r, and then plus c. We need this to equal 0. And so now this is the characteristic equation for the Cauchy Euler equation. All right, the characteristic or auxiliary equation. And so if we have a Cauchy Euler equation, we make the assumption that y equals x to the r, our auxiliary equation becomes ar squared plus b minus a times r plus c equals 0. And this, maybe it factors, maybe it doesn't, but we can certainly analyze it with the quadratic formula, which would tell us then that r is equal to the opposite of b minus a plus or minus the square root of b minus a squared minus 4ac over 2a. And depending on the discriminant, depending on what's under that radical, we can get three different cases. One, if the discriminant is positive, a second case if the discriminant is 0, and a third case if the discriminant is negative. So now let's take a look at those cases and see what happens. Alright, so let's look at the first case. The first case is if the discriminant, the b minus a squared minus 4ac, remember that was what was under the radical, if the discriminant is positive, this tells us that we have two distinct real solutions, R1 and R2, where they are not equal. R1 is not equal to R2. If that's the case, then we get, then we would have linearly independent solutions, y1 and y2. So y1 would be x to the r1, and y2 would be x to the r2. And so then we would have our general solution, would be y equals c1 x to the r1 plus c2 x to the r2. So distinct real solutions, that's the easier situation. c1 x to the r1, c2 x to the r2, just following our assumption that the solutions were of the form y equals x to the r. Our second case is if the discriminant is equal to 0. So if the discriminant is equal to 0, then we have two solutions, but there's a multiplicity, right? So we have one solution of multiplicity 2. So then R1 is equal to R2. Now remember, this means that if we said y equals x to the r1 and y equals x to the r2, since r1 and r2 are the same, these are not linearly independent. So like we did for the constant coefficient equations, what we would do now is use reduction of order, with our assumed solution y1 is equal to x to the r1 and find the v of x. It turns out that the v of x, right, so we find that the v of x is equal to the natural log of x. So our general solution then is y equals c1 x to the r, I'll say r1, plus c2 times the natural log of x times x to the r1. And this would be a good exercise for you to try on your own. Could you follow the reduction of order process with the general Cauchy Euler equation form and find that second linearly independent solution using reduction of order? It would be an excellent exercise, maybe a good bonus problem on a test or something. Who knows? And our third case is what happens if the discriminant is less than 0. So if the discriminant is less than 0, then my r values are equal to, they'll be equal to some alpha plus or minus beta I. And so we use some trickery here. We have to rewrite some things. We're going to have to use the fact that x to the r is the same as writing e to the natural log of x to the r. And we use a similar process as what we did for the constant coefficient equations, and through a good amount of manipulation, and again, this would be a nice exercise to try on your own, we end up with the solution that y equals x to the alpha times c1 cosine of beta times the natural log of x plus c2 sine of beta times the natural log of x. And this is a fairly messy derivation. It takes a few steps. It's not incredibly difficult once you sort of use this little trick that x to the r is the same as writing e to the natural log of x to the r. Then it sort of follows what we did for the constant coefficient situation. But again, this would be a good thing to try on your own and see if you can get to that end result, that if we have complex conjugate solutions of the auxiliary equation, we end up with this form. All right, so now let's actually solve some equations. All right, so here we're asked to solve x squared y double prime plus 3xy prime plus 4y equals 0. And I look at this and say, hey, there's an x squared and a y double prime. There's an x to the first and a y prime. This is a Cauchy Euler equation. So this is Cauchy Euler. All right, so this is Cauchy Euler with a equal to 1, b equal to 3, and c equal to 4. Now remember, when we write the auxiliary equation is ar squared. So the auxiliary equation is ax, I keep saying x, ar squared plus b minus a r plus c equals 0. So then, making the appropriate substitutions, a is 1, so r squared, plus b minus a, 3 minus 1 is 2, r, plus 4 is 0. So now I solve this auxiliary equation. Let's see, factoring won't work. Let's apply the quadratic formula. So then r would equal, let's see, negative 2 plus or minus the square root of b squared is, 2 squared is 4, minus 4ac, so 4 times 1 times 4 is 16, over 2 times 1 is 2. So r is then equal to negative 2 plus or minus the square root of negative 12. Uh-oh, that's going to give me complex solutions. Square root of 12, that's 2 root 3. So I've got negative 2 plus or minus 2 root 3i over 2, and so that's negative 1 plus or minus root 3i. So I see that I have complex conjugate solutions of the auxiliary equation, and we were starting with the Cauchy Euler equation again. So what that tells me then is the solution of the equation would be y equals x to the negative 1, x to the alpha, and let's put some brackets in here. Then I have a c1 cosine beta root 3 natural log x plus c2 sine parentheses beta, again root 3 natural log x. And so there's the solution of that Cauchy Euler equation. Here's another example. This would be a good one to pause and maybe try on your own. All right, so I analyze the equation. I see the x squared y double prime, right? 2, 2. X to the first, y prime, 1, 1. Hey, this is Cauchy Euler. Cauchy Euler with a equal to 2, b equal to 3, and c equal to negative 15. And when I then go to the auxiliary equation, I again remember it's a r squared plus b minus a r plus c equals 0. So that's 2r squared. B minus a is 1. So plus r minus 15 is 0. All right, now let's see, 2r squared. This one does factor, but if you're not good at factoring, you could still apply the quadratic formula. So let's apply the quadratic formula. R equals -1 plus or minus the square root of 1 minus 4ac. 4 times 2 is 8 times -15. That's going to be a plus. Where am I? Plus 120 over 2 times 2 is 4. So then r is equal to -1 plus or minus the square root of 121 over 4. R is equal to -1 plus or minus 11 over 4. And we break that out. We're going to get distinct solutions. Let's see, -12 over 4. R1 is -3. And -1 plus 11 is 10. 10 over 4 is R2 is 5 halves. Distinct real solutions. This is the simplest case. And so then my general solution would be y equals c1 x to the -3rd plus c2 x to the 5 halves. All right, and one more example, and again, this would be a good time to pause, maybe try this one out on your own. Again, this is a Cauchy Euler equation with a equal to 1, b equal to -7, and c equal to 16. And so then writing the auxiliary equation, I would have r squared, 1r squared, plus b minus a. Now b minus a in this case would be a -8. So minus 8r plus 16 is 0. Oh, that's a perfect square trinomial. That factors as r minus 4 squared, and so I see that r equals 4, but multiplicity here, right? Multiplicity 2. So this is that situation where we have the repeated root, and if we apply what we saw in the previous slide, we get the general solution. That y is equal to c1 x to the 4th plus c2 natural log x times x to the 4th. All right, so that concludes this section on Cauchy Euler equations.